Okay, so I think I might just begin the presentation. So today I'm going to be talking. Oh, can everybody hear me, by the way?
Yep.
Yeah.
Okay, so
I thought I
today
was
I'm
going
going.
crazy for a second. I was like, I can't hear anything
Oh
before.
yeah, sorry, I was muted. So today I'm going to be talking about a paper called "Attention is All You Need," and this paper is quite famous these days in the computer science field, and specifically in natural language processing. Um, so I wanted to talk about it today. And this paper came out in 2017 from a team at Google Brains. Even though it's called Vaswani et al., it's all the authors on this paper are first authors, and it was presented at NeurIPS. And since then, it inspired a lot of buzz because there were some new models like BERT and GPT-3, which came from OpenAI. And I guess it created a lot of hype around transformers and um, in natural language processing. So I also just want to say that this paper itself was quite short. I think it was only 8 pages, but it was very dense. So um, I will try to go through everything, but I don't know if I can finish everything today. So if I don't, then we can just have a second part. And I think I also need to start with the motivation of why they even bothered to make this model. So we need to go back to basically another paper and the history behind it. Okay. Oh, I guess Arvin left. That's fine. So if you have any questions, please feel free to ask at any time so that nobody's bored like halfway through the presentation. Okay, so let's talk about the motivation for this paper. So at the time, in 2017 when this paper was written, at the time we should understand that in natural language processing circles, one of the big challenges was doing translation from one language to another. So for example, like French to English or German to English, something like that. And there was a paper that came out in 2014 that reintroduced this concept of attention and using attention to solve this translation problem. And so to describe this paper, I will kind of give a little history of what people have been using. So kind of in recent times, people kind of found that using recurrent neural networks turned out to be something really useful for dealing with natural language processing problems. So in a standard neural network, we typically have this input and then we have some output that comes out. And in most cases, that's all we want to do. Like there's no other correlations that we need to deal with. But in the case of some some types of sequences, like a time series or sentences, then we might find that there's a certain correlation between different elements in this sequence based on where they are in space. And they're, for example, might be more likely to get one word given that we have this other word here. So if you worked with Markov chains, then that's probably something you're quite familiar with. So a recurrent neural network is kind of reminiscent of that idea. If you unfold the network, you will see that there is basically a chain of networks that are all connected together. And each network is represented here as H, and we call that a hidden state. And this is a whole network. And the way it works is that there's an input that goes into a hidden state, and then an output is predicted. And then when the next link of this chain, another input is given, and then this hidden state takes both the information from the input and information from the previous hidden state to come up with the output. So if we think about an example sentence, let's say we're translating from German to English. So we have this sentence, ich will nicht schlafen, and then we translate it to, I don't want to sleep. So in the case of using an RNN, what we would do is each word would be given as an input to each link of this network. So each will be fed into this first hidden state and it will return I. And so basically each position of the sentence will take in the input sentence or input word in German and will give out the output word in English. But there's kind of a challenge to this. So if you see in this case, ich will nicht schlafen, in German, this literally translates to I want not sleep. But in English, we say I don't want to sleep. So we put the negative before the verb. So in a unidirectional RNN, the model would never see the word nicht before it would see the verb. And so this scenario would never actually happen in an RNN. It wouldn't be, in a unidirectional RNN, it would never be possible. So at that time, they started to introduce a bidirectional RNN. And so the point of it is that not only do you go this direction through the sentence, but you also go back through the sentence. And then your output would be influenced by both of the feature vectors which come out of the hidden states from each of those directions, as well as the previous output. So does that make sense so far?
So I have a question, like, can the hidden state only look at the word that's, so in bidirectional, can it look at all words or just one word that's previous or in front of it?
Yeah, that's a good question. So it would only look at the word that's well, in the bidirectional one, this word would only look at the word before it in that direction, okay. And this one would only look at the word before it in that direction. And that highlights one of the problems with using RNNs, which Badenau et al. Tried to solve. So basically, the issue is that when you're working with RNNs and LSTMs, which are called long short-term memory networks, try to solve this problem a little bit, but they still have an issue with long sentences. But basically what problem you have is kind of what's called a short-term memory loss. So what happens is that when you get to, for example, this word schlafen, which is at the end of the sentence, it turns out that it basically gets the feature vector which comes from the previous word nicht. And in theory, that feature vector should carry some information about the node before that, which is will, but over time, this memory decays very quickly. And so in practice, it turns out that most of the time, the memory of a recurrent neural network only goes back to about the last node, and only a little bit is retained from previous nodes. And one way that LSTMs try to solve that is they have some gates. So they have like a forget gate, which tries to forget information that's not important. But still, it only can remember back around 5 to 10 nodes. And so basically the suggestion that Badenau et al. Had, so Badenau was he was a student from Germany. He went over to work with Yashua Bengio in Montreal, and he suggested that let's take this same RNN concept, but let's add, instead of just having each hidden state predict the output for a single word, let's add a weighted system that can take in all of the feature vectors which come from each of these hidden states, and let's weigh how important each of these feature vectors are to the final output. And then this final node can take in a weighted sum all of the feature vectors which came out of this network and use that in order to calculate what the best word is. And so since it's a weighted sum, for each of these output nodes, the weights are going to sum up to 1. But it turned out that this method was very successful, and it can remember word connections in very long sentences, and this was something that wasn't possible before. So this is the concept of an attention system, and this was basically just a fully connected neural network which was added onto this RNN. Okay, so now that we've got through that, this method was really useful, and it was very popular at the time, but there was a downside to it. So if you look at the way this network looks, it's very sequential, and because of that, it requires a lot of time to compute, and it also requires a lot of computational cost. And so, and this comes at the advantage of getting this contextual information about what words are next to you in a sentence. And so basically the authors of the Attention is All You Need paper, they suggested, why don't we just ditch this whole paradigm of using recurrent neural networks, and let's focus only on using attention. And so that's why they call it Attention is All You Need, because they believe that if we only focus on a model that's based on building this attention network, then we no longer need the recurrent neural networks that we were using. And the advantage of this is that they argue that they can dramatically cut down both computational time and computational cost, because they basically run all of the processes in parallel, and they don't need to do this sequential processing anymore. And they claim that they could train a model based on this Stanford translation data set in as little as 12 hours with 8 GPUs. Okay, so now that we have the motivation, let's look at what the transformer looks like. Okay, so this is a figure that they show in the paper, and we'll go through it kind of one by one. So first, let's take a look at this transformer. So the transformer is based on an encoder-decoder structure, which means that we take our input and we convert it into some kind of vectorized form. And then in the decoder, we take that kind of vectorized feature vector, and then we output our word. So, and let's keep in mind again that the problem that we're trying to solve is we have as input a word that's going to be either in like, a sentence, which will either be in like French or German, and we want to output the sentence in English. And so in this figure, we have this giant box here, and each of these giant boxes represents a single layer. So in the encoder, it says n times this box. It means that there are n times this layer. So in the paper, they suggest using n equals 6. So they have 6 layers in the encoder and 6 layers in the decoder. And within these layers, they have what they call sublayers. So there are really only 2 sublayers to get to know. One is a multi-head attention sublayer, and the other is a feed-forward network. And then we have these add-in norm sections, and these are just residual connections, which we talked about in a previous seminar. So let's go through each of these. Okay, I'm gonna start. Oh, so here's an alternative view as well. So this is to show what it looks like. There are the 6 layers in the encoder, which pass serially, and then this encoder returns a context shape, which goes to each layer of the decoder. Yeah, and we're translating from French to English.
I have another question. So before this, people used like a weighing fully connected network to assign weights to different words and then assemble them at the RNN, right?
Mm-hmm, mm-hmm. Yeah.
And I don't understand if their whole point is we don't need RNN, then how are they assembling these words?
Yeah, so I'll go through the whole presentation, and then
Okay,
if you're still
sure.
confused about it, because yeah, it's a long explanation.
Okay, right.
Okay, yeah. So yeah, let's start with the inputs. Okay, so here's some kind of background of how people process sentences in natural language processing. So usually as input, we have some words in a sentence and we want to basically turn it into a vector. So in natural language processing, they usually turn these words first into what's called a token. And to understand what a token is, we can imagine that we have a dictionary, let's say of like 10,000 words. And one of these words would be the word thinking. And so whatever element of this or position of this word in the dictionary, that index would be the token of this word. So now we've turned a word into a single number. And then now we want to turn this number into a vector. And so there's a system called word embeddings where they basically turn a number into a vector. And you can choose how large you want this vector to be. But the point is that for each number is represented uniquely as a vector. And so in this case, in this paper, they chose an embedding size of 1 by 512. So that's what, so now the input went from a word to a 1 by 512 vector. Okay, and now they add something called a positional encoding. And so this kind of tries to address one of the advantages of the recurrent neural networks is so in the recurrent neural network, we have an understanding of the position of words in a sentence because we get the previous word as input. And so this was their way of kind of trying to address that. If you see other people talk about this, they kind of argue that positional encoding doesn't really do that much, but I'm not sure myself. But so basically the positional encoding will be a vector itself, and it represents the position of this word in the sentence. And the positional encoding is simply added on to the embedding. It's not concatenated, it's just added on. And the way that we can think about this is, so actually in the paper, they suggest that you yourself can use your own function for positional encoding, but they suggest themselves what they used, and they basically tried two different equations that had to do with sines and cosines. And the abstract concept of this would be something like, if we imagine this position of this word, we would be able to find that, for example, hamburgers was closer to eat in the sentence than the word dinner. And that's kind of an abstract way to look at it because it actually looks more like this. So if you graph the positional encodings from the paper for 10 different positions, you will find that this is a visualization of what the positional encoding would look like. Okay, so to reiterate where we've gone from, we started from—
I'm sorry, Alyssa, can I ask a quick question? So
Yes.
this is very interesting. I just want to make sure I understand it. So go back a couple of slides where you talk about the token itself, right? So the original token, the 512 dimensional token.
Well, it's an embedding. So the token—
Sorry, right. It's an embedding that is a consequence of its position in the dictionary, correct?
Yes, yes.
Okay. And the next one, which is the positional component,
Mhm.
is indicating where it occurs in the sentence?
Yes, exactly.
Okay, so the fact that this you have 0011 and this kind of numbers, is there a generating basis for these numbers, or how is it manufactured?
Yeah, so it's generated from these equations up here. Where I'm indicating.
Right.
Yeah, so
And what is the support of this? So it looks like it's a, why did they pick a, I guess, sinusoidal curve, and what is the point of, how would you compare the extent of the x-axis with what you see in the sentence? How can you, just trying to get a sense for
oh,
it.
you mean from this graph?
Yeah, I mean, when you go from, how do you go from the sentence to this sinusoidal
Yeah.
curve to this representation you're showing us on the screen right now?
Yeah, so actually, my description here is kind of abstract. It wasn't exactly so. Actually, what's really happening in this function is that you're getting a function of a wave, and so you can kind of see that here. That if this is a 512 dimensional embedding, then you'll have a 512 dimensional, basically sine wave, and of slightly different frequencies. And so that's why you get something that looks like, so this, in this case, their embedding is about 64 dimensions.
Right.
And then, and this is the values of the vector of each element of this 64 dimensional embedding. And so it's just showing that there's you can see, well, it's hard to see it as a sine wave, but if you graphed this, it probably looks like a sine wave that dies out.
And then the embedding dimension is consistent that I get, and the tokens are what? The different words. So there are 9 different words.
Oh yeah, so
10 different words.
yeah, they're just 10, the position of, so this is like the position of the fifth. I didn't make this chart, but I don't like how this person says token position. It just means position of the word in the sentence. So this is like the 8th word of the sentence, the 9th word of the sentence, or sorry, this would be 10th word of the sentence, 9th word of the sentence, for example. This is what their positional embedding would look like.
So they've converted a sentence into a temporally encoded sequence, where
Yes.
the embedding dimension is consistent, but the position along the temporal axis describes where it occurs in the sentence.
Yes.
Okay.
And then they just added on to the embedding. So I think they just assumed the network will figure out, will basically be able to separate somehow this encoding from the embedding.
So the embedding is static. The encoding is dynamic.
Yes, that's correct.
So it's like an AC plus DC component then to the signal.
Yes, but of course, I mean, the words also change based on what the sentence is. So I guess.
So the embedding dimension is arrived at independently before it occurs in a sentence, right? It's obtained from the global dictionary, correct?
Yes, exactly.
And the encoding is specific to a sentence that you're trying to translate.
Yes, exactly.
Okay, got it. Thank you.
Okay, so yeah, so to reiterate that, so we have the input sentence, we tokenized it, we turned it into a vector representation, which is the embedding. So it's a 1 by 512 vector, and then we add on the positional encoding. So now each word is represented by a 1 by 512 vector. And yeah, these arrows shouldn't be there. I also didn't make this image, but yeah. Okay, so let's go on to the attention sublayer. And this is the meat of the transformer. So it's okay if we go through this slowly. So so basically this attention sublayer to me was presented in very abstract terms. So they try to rationalize what is going on in the attention sublayer. But we should note that even though they talk about these things like queries, keys, and values, all of these are basically just trained weight matrices. And so they might not have any contextual meaning to them. But the way that the authors present the concept of this multi-head attention sublayer is this idea of queries, keys, and values. And I like to think of this like a lookup. So you can imagine that you have some dictionary. So this is English to Korean. So I have a dictionary, and the key would be the word in English, and my value is the word in Korean. And then I have a query, and I request my dictionary to return the value based on the query that I've given it. So I give car, for example, it looks up car, it finds 자동차, it returns this word. So that's the value.
So I have a request for you, Elisa. I think you are sort of perfectly the person to answer this question for us. Is as you're talking about this paradigm, which is very interesting, by the way, can you, if possible, connect this to some notion of linear algebra, for lack of a better word, right? Like, for example, I mean, the way you're talking about this is basically a weighting matrix that's, one where the word is the key exists and zero everywhere else. And you basically do a multiplication between that matrix and the original matrix, which is, and then that way you get a y is equals a times x kind of situation, right? If you can, as you're going forward, if you can help us map this notion of attention to something that involves weight multiplication or matrix multiplication, please teach us that as you're going along.
Okay, yeah, I actually in the next slide, I'll do that. Yeah, I won't tell you the shapes yet. So it looks like a matrix here, and actually the paper itself is extremely vague about the shapes of what is happening in this transformer, which is why I have another slide later that goes through all the shapes. But let's think of it like a matrix for now. So yeah, you can kind of liken this queries, keys, and values process to just simply matrix multiplication of the query times the key, and then they normalize it using this is the dimensions of the key, and then they do a softmax and they multiply it times a value matrix. Excuse me. And so yeah, so basically this multi-head attention has, it's called multi-head attention because this process, this attention calculation happens h number of times. And so in this paper, they suggest h equals 8. So that means that there will be 8 different heads on this attention network. And so this image here is just a picture form of this equation here. But basically we multiply this query times the key, we take a softmax, and then we multiply times this value matrix. And yeah, let me go through the next slide. So if we think about, one second, if we think about where the embedding or where the input is going to, so the input basically becomes the query keys and values in the first layer. And so this query keys and values is multiplied by these projection matrices to become, it basically becomes a new query key and value. And then we basically calculate this attention for each of the heads, and then we concatenate them. So we basically put them back to back, and then we multiply it by this other projection matrix, which basically tries to return everything back to the size that it was in the input. And so the goal is that the output of this multi-head attention network should have the same dimensions as the input that came into it.
Okay, this is interesting. So hold on, go back one slide. So what you show on the left-hand side is a scaled dot product attention concept, right? And now when you say multi-head, is this basically now being repeated 8 times? Is that the idea? or something else is going on?
So it's not, so this scale dot product attention is happening 8 times, but this projection matrix is different for each head. So you're going to have different calculations that are occurring in each head.
Okay, go to the next one.
Mhm.
Okay, so head sub I is attention of, so how is the attention function defined?
So attention function is
Oh, there it
defined.
is, okay.
Yes.
Got it, okay. So now go to the next slide. Okay, thank you. I'm sorry, I'm taking a little bit of
Oh,
time, but I
no,
want
no,
to
no.
make sure.
No worries.
Okay, so the attention function is defined like this. Projection of parameter WQ, which is D model DK.
Yeah, so that's just defining the dimensions, but
Yeah. What is D model and what's D sub K?
so D model would be the size of the embedded vector. So it'll be 512 in this case.
Okay, got
And
it.
then dk in this case will be equal to 64 because they want to take D model divided by number of heads. So that's
Okay.
how they calculate
So
it.
512 divided by 8 is 64. Okay. Then you have 3 ones. You have Q, K, and V. So Q is query key value. The query is D sub K. K, is it D sub K or D sub Q? Or D sub Q is
D sub k. Yeah, so
okay.
yeah. Yeah, the query and keys should definitely be the same size.
The
And
same size.
the value matrix doesn't have to be the same size, but everywhere that I've seen the value matrix, it's always been the same size as the queries and the keys.
So remind me in your English to Korean example, the query was the word in English, the key was the mapping between the Korean equivalent and the English equivalent, and the value was the Korean equivalent.
Yes.
Okay. D model, okay, DV. In this work, we employ 8 parallel attention heads. For each of these, we use D sub K equals D sub V. I see. And D model by 8, okay. Okay, and so we take the attention function and which is head sub I and then concatenate it 8 times.
Yes, we
The
basically just put
output
them all
of the,
together.
okay, and then W sub sub O is H times DV because there are H heads, okay, DV times D model.
Yes, so that
Okay,
brings us back to our input size.
got it. And this brings us back to our input side. Why is that? Because D model was 512.
Yes. So we
DV,
originally had a, well, if we think about it in terms of matrices, let's say we have S times 512 to begin with. So this should return us back to S times 512 at the end, if S is number of samples.
so the multi-attention network is working, is generating as many, is it doing it for the whole sentence or just or doing it word by word?
So can I answer that in a later slide?
Okay.
So because this is quite confusing, right? Like this is what I also had gone through, but I think it's best if I explain all of that in one chunk.
Okay. Fair
Yeah.
enough. All right.
So so let's think in overall terms of this kind of concept that the multi-head attention layer, it calculates some linear attention equation, and then it outputs the same size of what we got in here. So, okay, so next we have this feed-forward network. And this feed-forward network is simply a fully connected neural network, and it's only 2 layers. It's very simple. It has a ReLU activation in the first layer, and then it just has a residual connection at the end. And then as an output, what we get is this context shape. I will call it a shape, Z. And so here's where Z is in this diagram. And if you'll notice too, this becomes, so this is so they don't label it here, but this is supposed to be on the rightmost. That's the query, the key, and the value. So actually this context shape becomes the key and the value for another head in the decoder. And so in the decoder,
It becomes the query and the key.
it becomes the key and the value, actually. The query, I don't know if I said that wrong earlier, sorry. The
No, you
query,
say it correct. I'm just trying to understand.
oh, the query comes in the decoder. The query in this multi-head attention sublayer is going to come from somewhere else. So what's important to take away from this is that there is a context shape. So basically, to go back, like to look at the big picture. So this encoder is basically trying to take our input word in French, and then it encodes it into a into what we call a context shape. And then this context shape encodes all of the information we have about the word in French. Okay, and so the decoder is basically involved mostly all in English. So decoder only cares about English, but decoder gets some help from this context shape, which is some encoded representation of French. So that's where we're at.
Okay.
And oh, any questions? So the decoder looks almost exactly like the encoder, except that it has an additional sublayer, and this is where the arrow is pointing. This is the additional sublayer because it takes in this context shape, and it tries to use it to predict the next word. So I won't go through I'll go through specific parts of the decoder now, because we already know how multi-head attention works. We know how this feed forward works. So let's first take a look at what the decoder does. So this is only in testing. So what we see here is that the encoder has done its job. Once the encoder is done, it's completed, it doesn't go back to the encoder. Everything in the test part, now that I've converted my sentence from French into my context vector, only the decoder needs to work now. So the decoder in the test set is going to work step by step. So it predicts the first word, and then it puts the first word back as a previous output into the decoder, and then it predicts the next word, and then it takes those two words, puts it back into the decoder, and predicts the next word. Does that make sense? So this is only in testing.
So the animation is maybe going a bit too fast for me. Let me try to understand.
Yeah. So only we only see the decoder working here, and the decoder is spitting out one word at a time. And
the next word, right?
Yeah, spitting out the next word, and then it's putting as its previous output. It's putting in what it has already predicted, and then it will predict again, and then it will return this everything it's predicted again into the decoder. And so,
is it a way for so let's say the second word was outputted incorrectly. There is no mechanism for back propagation, correct? It is what it is.
Yeah, it is what it is, basically. Like,
so
what,
basically, if you have
this is in testing, so we haven't talked about.
Of course, but I'm saying that in testing also, if your first prediction was incorrect, then the next prediction is likely to be incorrect too.
Yes, that's true in translation.
Okay. Yeah.
Well, I guess it would depend, because if you said, for example, I want a blue cat, but instead it translated blue to red or something like that, then I guess that wouldn't really affect the word cat, because it's just another adjective. So I guess it depends.
True, but I guess what I'm asking is the support or the history that is being used to make a prediction of the future, is that a single point back or many, many points back? Or if it's many points back, then does the attention function actually tell you which parts to focus on?
Yes. Actually, yes. So it does all the positions of the sentence in the, so let's say the previous output is now I am a. So for
Okay.
the decoder to look at student, it will look at the whole
History.
sentence, of what it has previously said, and then it will focus attention on what, or in theory, it focuses attention on what's important from what it already said, and
Okay,
then it will use that to output the word student.
got it. Okay, that is very helpful. So obviously, so even if your next prediction is incorrect, it doesn't matter at some level if the context has been transferred correctly and if the entire history has been used to make the next prediction.
Yes.
Okay, got
Exactly.
it. Thank you.
And I think it's also something that might be interesting or useful to note is that the models that are built today using transformers like GPT-3, for example, is not a translation model anymore. Now it just gives you like you could ask it a question, or you could tell it something and then it will respond to you. So I guess in those models, what's important is to be to make sense contextually. And so this kind of issue of like a few words being messed up is not as big of a problem in that context, I guess.
Mm-hmm, mm-hmm.
Okay, so
thank you.
Decoder, what it looks like. All right,
Okay.
so now the unique part of this decoder is really this sublayer that I want to talk about. It's the masked multi-head attention. And it looks just like, if we go back to this attention slide, it looks just like the attention sublayer, but we have this optional mask here. And while it's not optional in this sublayer. So this is where we start talking about shapes. And so this is where it might get more confusing. So here's a sample mask for a sentence which has 10 words. Oh, first let me go back. So let's note where the mask is. So basically, once we multiply this query times the key, then we implement the mask before doing the softmax function. So that's where it's used. All right, so here's a sample mask for a sentence with 10 words. This is what it looks like. And it's binary, so black is 0 and this white space is 1s. And the reason why they decided to use masks is because of this reason. So let's talk about how the decoder works in training. So if we think of a sentence like this sentence, which has 5 words in it, and in French, we have the input that we're given is je veux un chat rouge, and our label, or what we want to output, is I want a red cat. So what we can actually do is we can turn this one sentence of 5 words into 4 different examples. So the encoder input will always stay the same because the encoder input is just simply the French sentence turned into some kind of feature vector or feature matrix. And the decoder, we can get new examples from the decoder. So we can turn this sentence into 4 different examples because we have an input as, for example, we want the label to be want. If our input is I want, then our label should be A. If our input is I want A, then our label is red. So for example, and so basically what we're training this model in the training step is we're saying, if you see a feature vector for je veux un chat rouge, and you see also the English words I want A, then we're training the model to say, well, then your label should be red. Does that make sense? So I see a feature vector that represents this, and I see also an English part of a sentence which says, I want a red, then I want my label to say, I want the output of the decoder at this point to say cat.
But the placing of the words, the last two words, has been interchanged between French and English, right?
Yes, but
So how does, I mean, just wondering how that works, because is that, so is it learning the intrinsic mapping in syntax between two different languages? Is that the expectation once you see enough sentences?
yeah, I guess what it's what it's kind of saying is like, if I have a model and I said, and I gave the model, I want a red, and the model has to figure out a red what? Like the label, it doesn't, it could be a red dog, it could be a red hot
Right.
dog. And but it gets also this information, it gets the whole sentence, but in some feature vectorized form that's encoded.
No, I think the first two and the last problem is much easier to solve than the third problem, because there you went from cat, from it's in French it says cat red, and then in English says red cat,
Mhm.
right? So the fact that it knew to flip this in the order of the way subject object things happen in different languages, to me that's very interesting, right? So somehow, I mean, I know this is all in testing, but
Yeah.
but I guess it learns from the attention is how to place the attention on the right. So in some sense, what am
Yeah.
I saying? I have to be careful what I'm trying to say. In some sense, the mask that you're talking about is acausal when you go from English to French, from French to English, because you had to look ahead to know that you wanted a cat. I mean, you
So
wanted something red. You wanted something red.
yeah, so actually this mask is only placed on the English words. So you get the entire French word. And so in theory, in the attention head, in the attention sublayer, it should focus, it should weight higher this word like whoosh, for example, than chat. And then it will that's why you will know to output red. But the point of masking is, if we imagine that we have a 10-word sentence, and then I repeat this sentence 10 times. So I overlay a 10-word sentence onto this mask.
Mm-hmm.
Then we can see that like this would be I want a red. So it's basically creating this decoder input.
Got it. So the masking is on the output side. That's correct. You're right. I
Yes.
forgot that. It's the
Yes.
decoder. And so
Yes.
it's like output regularization in some sense. You want the output of the encoder decoder architecture to follow a prescribed pattern.
Yes, and you also you don't want, because you don't want the model to know what the next word is before it guesses it. So that's why, like, I want to mask cat, for example, here, because I want the model to predict cat, and I don't want it to know that cat is coming next, right?
I see.
So that's why we do mask.
Can you have acausal masks as, I mean, this is a causal system, right?
I guess so.
That's what your previous slide said, right? It's autoregressive and you're ensuring that there's causality to it.
Mm-hmm.
But what I'm asking is, can these masks be made acausal? Which is, can you look? I'll tell you why I'm saying this. Look into the future, right? Because in the case of the English translation, the fact that you can know that you're going to be saying cat in the future constrains the space of what you're going to be saying right now. Right? That's how it happens when we express ourselves. That's what we do, right? We have the subject and the object in our heads, and everything else is basically conjunctions.
Yeah, so that's a really great question, and this actually goes to so I think, for example, what you might be saying is that for example, in a question answer scenario, it might be useful to know some context of what might be said in the future in order to know in order to know what you want to say now, in a way. And so
Right.
BERT, it stands for bidirectional encoder representations from transformers. Basically what BERT does is it changes up this mask. So instead of having this lower triangular matrix structure, it basically randomly unmasks different words in the future. And so you don't get the complete sentence, but you get some context from future sentences. And that helps, it helps the model to provide a better context for what it's going to say. So
That's why bidirectional, because you can look forward and then look backward.
yeah, so
Okay.
yeah, this was the part, like this whole masking part was like the thing that bothered, like I couldn't figure out about transformers for a really long time, but.
No, this is very well explained. Thank you again. I apologize to those that may have taken the class and know this stuff, but I'm still trying to learn my way through this. So I appreciate the patience.
Oh, is there a class on this?
No, I'm just wondering, there might have been, I'm sure that, I know that all of you are taking all these classes in deep learning. I wouldn't be surprised if somebody's had a class on, all these different architectures and all the details. So for them, it might basically be, it might be pointless, but I'm just learning along as I'm going. Thank you.
So now let's talk about shapes, because when I read this paper, this was the biggest pain for me, was trying to understand what they were talking about without knowing the shapes. So I made these charts. So I have the encoder and the decoder chart. And I made these charts by using so there's an annotated transformer that comes out from an NLP group at Harvard. And they basically have a notebook of a transformer. It's their own version that they made. And in this example, they had 30 sentences, training sentences, and each sentence was 10 words long. And so if we kind of look at the shapes, we begin with this 30 by 10 matrix. But then basically the rest of the network is all tensors, which is why I didn't want to explain the shapes before. But once you turn it into an embedding, you have 30 sentences, each with 10 words, and each of those 10 words is represented by a 1 by 512 vector. So that's why you have this 30 by 10 by 512 tensor. And that's what you try to keep throughout this encoder. And so finally, this context shape is a context tensor, and it's the same size as our input.
This is wonderful. I'm just trying to follow through it. So it does 30 by 10 by 512. And as you say, after concatenation, you have arrows going down. Input after tension, after concatenation.
Yes, sorry. So yeah.
It should be going up. This should be the opposite way, right?
Yeah.
Okay, good. 30, 25, 12. Okay, 30 times 8 times 10 times 64 after tension equation, because your QKVs are 30, 10, 64. 30, 10, 5, 12, correct? 30, 10, 5, 12, and then you have 8 heads. So that makes it, and then you have 64, because 64 divided 5, 12 divided by 8 is 64.
Yes.
You just broke up the 5, 12 into 8 times 64.
Yes.
And that gives you parallelization, fine. But the matrices are, the size of the vector is still the same. It's still 30 times 10 times 5, 12, right? On the left-hand side. It's just resized in some sense.
Yes, I believe so.
Okay, so after tension equation, now that goes back here. That gives you 30 times 8 times 10 times 64. Then you concatenate it like you had planned. That gives you 30 times 10 times 5, 12. And then you have feed forward. Okay.
Yes, and then you get this context vector, and then this is a decoder. So the flow goes like this. So we input here, we go through these attention heads, and then out. So one thing to note is that the output size is a little different. And so basically what they did, or what they do here is, so you had a 30 by 10, so you had 30 sentences, 10 words each. They basically just cut off the last word from each sentence. So why would they do that? The reason is because when I send this sentence through the model, I don't care what the last word is in like as input, because you're trying to get the decoder to predict the next word, and there's no word that comes after the last word. So they just cut the last word off.
Okay. Okay, that's 30 times 9. And do the same process, 30 times 9 times 512. Where is the context vector entering?
It's
See,
entering,
okay, there it is.
yes. I assure you that, so it seems weird, but I did do the math on the matrix sizes, and it does work.
No, I believe you. I'm so glad that you worked through it, because this is so much more helpful. I appreciate this very much, because you're spelling it out for us.
A lot of work.
So everything is the same, but instead of 10 before, you have 9 now,
Yes.
right?
Yes.
And we understand why it's 9, because you're truncating the last one.
Yes, but then when the context vector is still going to be 30 by 10 by 512, but
Correct.
still when you go through the math here, you'll still end up getting a 30 by 9. Like they will cancel out when you multiply this. Basically, when you multiply this q times k times v.
Okay. Okay. And the output is 30 times t. What is t?
Yes, so t. Okay, so t is going to be the length of your dictionary. So if we remember from the very beginning, if we have a 10,000 word dictionary, then at the end of this, we're going to get a 30 by t matrix. And so let's talk about that. So finally, at the end of this decoder, we finally have this last linear layer. And the point of the linear layer is to just change the size from what we had as output from the feed forward network into basically a 1 by t vector for each sample, where t is going to represent the size of the dictionary. So they call it vocab size. And then we do a softmax on this, and then we get these probabilities for what the likely word is. And then they just take the max value, whichever the argmax for the highest log probability, and then they get an index into that dictionary, and then they come out with the word.
Very cool. Very cool.
Okay. So finally, let's talk about some.
So is the sentence, the output sentence is basically the map estimate, I would say, right? For these individual calls,
yeah,
correct?
Yeah, I guess so.
Okay. Okay.
Okay, so some results. So what did they actually do here? So they did this challenge where they used the that Stanford data set for English to German, English to French, and reverse, and they compared it with several other different NLP models at the time. And what they found is, at least to me, these numbers weren't that impressive. But I mean, they did better, but they didn't do wildly better. But their flops, the number of flops used to train is significantly lower, especially for the accuracy that they got in their blue score. But so this is the first transformer model, but later transformer models have done even better than this. So we can imagine that even though this result is not like blow all the other models out of the water amazing, it has created other models which have done really, really well.
So this part, thanks to your explanation, makes a lot of sense of how this is all put together. What did they improve conceptually in the future models that caused their performance to go up?
So one of the things was the masking. So BERT, basically BERT is the parent of all new NLP models that are coming out, and BERT was based on this transformer model. So you can't understand BERT unless you understand this, but BERT is really like where the main changes happened. So they
Okay.
another thing they also did beside masking was they changed the number of layers and I think a number of attention heads. But I'm not sure. I'll make another presentation on BERT later.
No, that's okay. I'm just trying to figure out where are the degrees of freedom that have led to the biggest improvement in the performance, right? Like, is it in having more functions like H? Is it in changing the matrices themselves? Like, the choice of W seems a little, strange to me,
Yeah.
right? I mean, why couldn't they have gone bigger or smaller? But I'm just trying to get a sense for that.
Yeah, they did actually try. So in this paper, the authors also tried to change up the number of layers. They tried to change the embedding size, number of heads, and size of the feed-forward network, size of their values and queries, keys, matrices. And they try to look at what would give the best score. But in the end, they found, I guess, these to be the best results. So it seems that there's a lot of hyperparameter tuning that is involved with this as well. So,
Yeah.
and then lastly, this is still, I just kind of figured this out this morning, but I still feel a little confused by it. But so here's some, they try to go into the encoder and then they try to show you, okay, so we have 6 layers in the encoder. This is the 5th layer of the encoder, and we're looking at two different attention heads. And we're showing you what attention scores most focused on in this sentence. I guess like I did the math, and I think they did it right about here at this step, because they can get a tensor size where if it's like a 10 by 10 sentence, or if it's a sentence with 10 words, they can basically get this like 10 by 10 matrix here times number of sentences. But I don't know. I guess it's I don't know what to think about it because it's very abstract, I guess. The idea of these values being attention values is still quite abstract to me. But here's another
So
example.
what is it saying? I'm sorry, I'm missing, I think, the key
Yeah.
point here.
So
What
what
is
it's
it,
saying?
top and bottom?
So oh, these aren't actually these are two different sentences. So the animal didn't cross the street because it was too tired. So how does it look at this sentence? Like what does it refer to? So they basically looked at the attention weights around the word it for each word in the sentence, and they found that that the attention weights focus the most on animal. And then we have another sentence that says the animal didn't cross the street because it was too wide. In this example, where we changed tired to wide, we see that the attention weights focus more on the word street than it did on the word animal.
Okay.
Do we, I mean, so do we think that this, so I've seen papers talking about how like in natural language processing, there's often this issue of like, if you just take whatever language exists out there, you'll get you'll get correlations between words where, yeah, I mean, street is correlated with wide, but like you can inherit a lot of biases if you don't think about like, it's like doctor is associated with man, and like these kind of, like if you see he, it's like, she is associated with nurse, right? Like you can, if we just go based on this, it's associated, these kind of words are targeted together, you build in those kind of things. Yes. I know that's not necessarily the scope of this, but like what do you think about that in this kind of attention-based context?
I mean, I think that's totally a problem, and I still think it's a problem today. Like if you even use Google Translate, there's some pretty well-known examples where I think what they were translating from like Russian to English. And then, so I guess in someone who knows Russian can correct me, but I guess in Russian they don't have like, there's no such thing as he and she. It's just one word for he and she. So they put in Russian, like blank is beautiful, blank is smart. And then when they translate it to English, it said she is beautiful, he is smart. So I think that is a consequence of what they were training their model on. And there's a lot of other really even more disturbing examples. There's like a game, I just read this yesterday. There's a game that uses, I think it uses GPT-3, and it's kind of like a, one of those like text-based role-playing games, but you can kind of like, it will generate the scenario. And because of what so many people have typed, it generated some very like inappropriate scenarios. So it is based, I mean, this problem is totally prevalent, still a problem, needs to be addressed by some ethicists, I think, on how to improve that.
Is there like a, I mean, like, should we be trying to build in more like for these known issues? Should we try to build in kind of like an understanding of what, like, you know, if we know that Russian has a gender neutral, like a gender neutral pronoun, right? Is there something we should be building in, like, at least for these very like like known areas of problems? Do you think we should build something, a module for that, or do you think we should train it in a way that we can decouple some of these? Or like, I don't know, like maybe that's beyond the scope of this, but like I thought it was interesting seeing this kind of association matrix, because that's one of the first things that popped into my head.
Yeah, I'm pretty sure Timnit Gibru would also agree with you, but I guess that people can build their own custom parts to it, but I feel like what it would take would be an ethicist who identifies where the problems are. And then I guess the easiest thing to do would be to try to make examples that would overcome that. But I don't know, I guess like there was another example too. It doesn't have to do with NLP, but it had to do with Google's image search, that whenever you searched CEO, basically it would only give you pictures of men. And then, but now if you Google search CEO, you'll see also pictures of women and diverse figures. I think that Google had to make some adjustments in their models, like maybe post adjustments to influence that.
I gotcha. Well, at least this highlights like where the attention will highlight kind of what it's pointing at, right? So that's a, without knowing what it's taking into account, you just get a result out, and you can only like look at it as a black box. So sorry for derailing things.
No, it's a good question. The last slide is just to show, so this is another example. So this is actually where they look at two different attention heads, and all they're saying here, so this is also the fifth layer of the encoder, two different heads. What they're just trying to show is that different heads focus on different things. So to show that diversity of attention heads is useful in this model.
So this is interesting. Now, could you go back to a previous slide? You mentioned something about you were not sure of what was happening, and you gave something about the M by M dimension. I'm
Right.
trying to see what is the connection you're trying to draw there.
All right. So I guess what was confusing me is that in order to build something like this, you would need, so the sentence is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is like a 12 element sentence if you count the period in it. So you would need a 12 by 12 matrix then, right, to know, because you need to know the association between each word and every other word. But when I went through encoder, when I went through these shapes, I don't see so that would be equivalent to a 10 by 10. I don't see a 10 by 10 matrix represented here, right? At least in the shapes that I've shown. So,
Okay.
but if you, so I basically I just did the math, like simple, like where did it go? The simple attention equation here, like this, and basically I think that you could get this 10 by 10, or it would be a 30 by something by 10 by 10 matrix, 30 by 8. You would get that if you just take this matrix before the softmax, before you multiply it times v. If you just take this, you should get, in my 10 word example, you should get a 30 by 8 by 10 by 10 matrix. So I think that's where they pull their weights from in this
This is
section.
looking at the correlation between what? What is the left and what's the right? I guess that's the point. The input and the output?
No, so this is supposed to be, this is the same sentence on the
But-
left and on the right. So that's what I'm saying. You need to have a matrix that has the relationship between every word and every other word in the sentence.
Across different attention heads.
Yeah, you should have one for each attention head, and you should also have one for every example sentence.
So I guess if you have to find this notion of which term is being influenced, that influence requires a lookup of the relationship between two attention heads, correct?
No. So, like, let me show it, kind of like use the mask as an example. So this mask is like a 10 by 10 matrix. So
Right.
if I had, like, I don't know, like a 10-word sentence here, and then I have the same 10-word sentence here.
Right.
And like, let's ignore the mask. Like, I'm just using this as an example for
Right.
a matrix. But then like the same sentence on both axes, then each number in this matrix would represent the relationship between like one word and all the other words
Based on
of
what?
that same sentence.
Or based on what? Because it's not like one's the input and one's the output, right?
No, yeah, it would just be the attention. Like, it's so this is the essence of attention, right? Like, this would be like how each word is related to another word. Like, if I see it, then I want it to focus on these words. Like, they will have higher attention scores.
Okay.
So
Okay.
we assume that we've trained this, like if the model is successful, that we have trained it as such to prioritize these words when we
Yeah, I guess where I'm getting confused is that this is almost like using this sentence to generate itself, right?
No, yeah, no. So they're in this case, they basically are going inside the network, and they're looking at, like, let's say maybe what happened, or maybe what's going on in the network as a whole is they're translating from like English to German.
Mm-hmm.
But they went into the encoder. So the encoder is only focused on English,
Mm-hmm.
right? So they went into the encoder, they went into one of the attention sublayer, into one of the heads of the attention sublayer, and then they looked at what the attention weights are doing.
Okay, got it. Okay. And your next slide, that's looking at
so this is two different attention heads. So in this
Got it.
case, we had two different sentences.
Okay.
Now we have two different heads for the
Okay.
same sentence.
So the weights are slightly different, is what you're saying.
Yeah, and so the point of this one is to show that we have two different sentences that are almost the same, but a human would contextually understand what the what it refers to, because we know what the tired and wide. And we're showing that the model can do that too. In this case, they're showing that different attention heads on the same sentence will be focused on different things. So basically this kind of debunks any thoughts that the attention heads are focused on the same, that you don't need a lot of attention heads. Like each attention head has its own focus, and having a diversity, like having a lot of attention heads brings some diversity to the interpretations, I guess.
True,
And
true.
I think,
But have you given any figure of merit that says, given if you know the length of the output that you're looking to predict, how many attention heads might you need to be able to do a reasonable job? Like for 10-word sentences, they're already at h equals 8, right?
yeah.
If you talk about now 20-word sentences, would it be 16? Would it be 18? And as the number of sentences, and paragraphs become bigger and bigger, what happens?
Yeah, I think, I guess this is where you just need to do a hyperparameter search. I don't remember what they use in BERT, but it seemed they used a lot more attention heads, and it seemed to be quite successful, but I don't know how they determined how many they should have used.
And yeah, and attention heads become an issue. I mean, you can almost imagine like a nesting structure, right? Where you have local attention heads for sentences, but you have somewhat global attention heads for sentences in a paragraph, for example.
Yeah, I guess so.
So and this is fascinating. Thank you for taking the time to explain this to us, Alyssa. Are there any more slides? I have a few more questions, but I want to make sure you got through all your slides.
Oh, I'm done. Yeah,
Okay, so thank you. So I have a very naive question. I'm almost thinking of this as like a pics to pecs scenario, right? Basically, you want to go from pictures taken in the morning to pictures taken at night, or you want to go from sketches of persons to real pictures. Why couldn't you simply use, and that's sequential data too, in the spatial dimension, in fact, it's in 2 dimensions. Why couldn't you use a conditional GAN kind of situation to do translation? Why would you need, what does this kind of architecture buy you?
Again.
Right, I'm thinking of 2 pictures, right? One's taken in the morning and you want to generate what the picture looks like at night. So the physics of the process, right? The structure of the building is the same, but its lighting and all that stuff has now changed between morning and night.
Well, I guess again looks very similar to a UNet, right? Like it's in the generator, it's all convolutional based, but in NLP you can't use, it's not an image, so you can't have convolutional filters. So I guess this is based off in NLP they have to work with like recurrent neural networks instead.
But you already converted that with that pictorial position encoding picture you showed us. There was a picture.
Yes,
right? There's a word and there's a position, and that's a picture. It's a 2-dimensional. It's an image, right?
I guess someone could try. Maybe someone could try converting words into. Well, I guess the other issue would be that sentences are really one-dimensional, right? But images are 2-dimensional, and so when you run a convolutional filter over it, you're looking at relationships in 2 dimensions, whereas that would be kind of like a sample contamination in NLP, wouldn't it? Because you don't care, each sentence is independent of the other sentence, and you wouldn't want some type of 2D filter to blend them all together.
I think you can go back and forth on that, right? Like you can, in a data rich setting where we had the luxury to be able to look at each data point independently, I think it's fine. But as you come into more specific settings where data is limited, you can think of clustering the sentences in English into topics, right? And topics are places where the distribution of word usage is consistent within the topic, right? And you can generate topic derived dictionaries You can derive and because you can do topic derived dictionaries in latent representation, my convolutional filter takes on a slightly different meaning. It's almost like saying the notion of proximity in x-axis is the proximity of two neighboring words in a sentence. But my proximity in the y-axis is proximity that is more related to words co-occurring with each other, right? I wouldn't be surprised if somebody came up with this notion where somebody came up with a convolutional filter that has different characteristics in the x and the y directions.
I guess so. It almost feels multimodal because your measurements on the x-axis and your measurements on the y-axis are actually different, right?
Correct. But the point is that the way we talk about kernel fusion and we say that you can have multimodal kernels where each kernel obeys the geometrical considerations of the domain it comes from. But then you can fuse kernels by doing kernel multiplication, right? You can do kernel fusion. So why not do kernel fusion? I mean, convolution kernels are basically that kind of thing, right? So you can multiply kernels. I'm just saying, right? I mean, there is no, once you decide that it's basically a picture, then the mechanics of what defines the proximity of pixels in a picture, that can be re-examined. But I almost see a physics, right? Because there's a physics between how an image looks like in the morning versus at night. There's a physics to how words that are given to us in French will map to how those words happen to be expressed in English. The physics of this is established. So I'm just saying, in a data rich situation, maybe we don't have to go that far. But we are now talking about data starved scenarios where you have to start interjecting the physics of the problem to constrain your need for data. Right? Yeah. So I was thinking out loud, right? Because to me this looks like a GAN. I don't see, I mean, like a conditional GAN. And I mean, there are some advantages, right? The attention, in fact, people are talking about now visual transformers, right? They're going from standard transformers to basically putting this. I would in fact recommend that, whenever your turn comes up next, right, that you take us from transformers in sentences to transformers in the visual world, because that was one of the biggest papers to have come in the past couple of years in CVPR and those things. So what did they do to convert the transformer interpretation from linear space to spatial context? Right?
Yeah, I am curious to know as well, because the model seems very tightly customized for this type of NLP problem. It's hard to imagine it with images.
Yeah, exactly. So I thanks to you, I can now buy the possibility of a transformer helping me to generate and translate sentences. But paragraphs are units of thought, and paragraphs constitute more than a single sentence. So the notion of attention now has to look not within a sentence, but between sentences that might be placed variably along a paragraph.
Yeah, so this is where BERT has helped. You can play around, for example, with, I think it's GPT-3, but you can basically ask it a question, or you could give it some type of prompt, and then it will respond with an entire paragraph. So yeah, they are kind of doing that now.
Okay. Yeah, I almost feel that when you want to go from sentences to images, and you want to use visual transformers, the fact that the scale of the image has a role to play in interpretation of the image, right? Like at one scale, you can make one sort of inference, but when you zoom in or zoom out, you make a very different inference, right? So the translation of transformers, like the way you've presented it, to the visual transformers like people are talking about these days, I am not able to see that conceptual leap fully yet. So I would, if somebody's taken a class in this, or if they have a turn coming up before Alyssa, maybe they could take a swipe at trying to present that paper. I think it's a very useful paradigm. Again, I'm not in the business of trying to create a new architecture. I don't think that's something that I can do very well. But I feel if we know the pluses and minuses of these architectures, we can use them more effectively in our problem. So I think it's good to talk about these.
Sounds good.
Wonderful. Any other? Everybody has been very, very quiet. I apologize for taking up all the questions. But does anybody else have any questions for Alyssa? Thank you again, Alyssa.
Yeah, my pleasure. So if there's no questions, I want to stop the recording.
Sure.